In Chapter 5, we're going to be looking at something else, the area problem. How do I find the area of a shaded region? Now, this comes from a bigger problem, right? If I want to know something like the area of a circle, right, we have a formula for that. And we have like the ancient Greeks to thank. They figured out area for circle. Squares are pretty easy, right? Triangles, okay. If I have a very regular shape, that's fine. But what happens if my shape is not regular? How do I find the area of this thing? Okay, and that seems like an important thing to know, and we can extend that, you know, to 3 dimensions. How do I find the volume of an object? That seems like an important thing to know, right? If I wanted to, let's say, design, you know, anything, right? A car, a boat, design, you know, pieces for, you know, a desk. You know, I want to be able to know ahead of time how big things are. Finding volume would tell me how much material I need, right? So, of course, in order to do any sort of modeling, it seems like you know, it's important to be able to figure out things like area. And this is one of our basic motivating ideas in calculus. How do I find area under a graph? And this is something else that we're going to answer. And it seems like this comes from a very different place than the tangent line problem. And then what we'll find out midway through chapter 5 is that these two are related, that solving the tangent line problem and solving the area problem are two sides of the same coin. In fact, they're the kind of like opposite directions. One of them is kind of almost like, you know, going backwards from the other. Okay. Um, so this is going to be solved with something called integral calculus. Okay, the tangent line problem is solved with differential calculus. Okay, and I'm gonna spoil the whole class for you and say these two are completely connected. The fundamental theorem of calculus connects integral and differential calculus together. Okay, and we'll look at that, but I feel like that's okay because nobody really likes surprises in mathematics anyway. All right, so that's kind of the overview of what we're going to be doing in calculus. Okay, and the idea of a limit is fundamental to solving both of these, right? So here, I think that we saw it a little bit with the differential calculus, right? Solving this tangent line problem. What I need to do is find points that get closer and closer. So you can think of the difference between 1 and my other number. I want to get infinitely small. How do I do that? And the limit is going to be our tool for finding things that are infinitely small. It's a little bit less obvious here how a limit is going to be helpful. And we'll talk about this when we get to chapter 5. But the basic idea is that I want to approximate this, right? So maybe I can break it up into pieces. And on each of these pieces, I'm just going to very roughly approximate it with a rectangle. Okay. And this approximation looks terrible. It doesn't really look like it's going to be very close. Well, it's a little bit close, but it's definitely off. But the idea is if I use more and more rectangles, I'll get a better and better approximation. So what I want to do is let my number of rectangles become essentially infinite, and then I'll get an exact fit. Okay, and again, this is maybe like the flip side of a limit. Instead of getting infinitely small, we want to get infinitely big, but we're still dealing with infinity. Okay, so limits are going to help us deal with infinity in both directions. Okay, so you can see, all right, if I add more rectangles, I now have a better fit. There's a little bit less, you know, overestimate, a little less underestimate with each one of these. And so I'm getting a better approximation. Okay. And that's how we go about integral calculus. Okay. All right. So that's kind of the idea behind what we want to do in 2.1. 2.1 is not a very complicated, you know, mathematically. What we want to do is set the stage a little bit, right?